Good morning. My name is Ed Brost, and I'm an associate with the Bowman Center for Sustainable Energy, which is an energy think tank based in Sarnia, Ontario, Canada. Today, I'm going to talk to you about hydrogen and specifically about a hydrogen project proposal. Now, we've been hearing about a hydrogen economy literally for decades. And in recent years, because of climate change concerns, we've been hearing about green hydrogen. The problem is that we really don't have a green hydrogen supply, not like we have a gasoline supply or diesel fuel supply. And why would we not have a supply? Well, because we really don't have a market for green hydrogen. Green hydrogen costs more than does conventional hydrogen. And so what we have is a classic chicken and egg story, which came first. Today, I'm going to talk to you about a project proposal to be located in Sarnia, Lambton that just might help solve this chicken and egg problem. Now, we're not talking about a pilot plant or a research project. We're talking about a large-scale project, a project that is designed from the outset to be able to access a low-carbon hydrogen market before these future green hydrogen markets emerge. Sort of a hedge. And once again, we're talking about a big project. This is not a commercial demonstration or a pilot project. What would it look like? Well, it's an assembly or a configuration of a number of well-known parts. We're all familiar with electricity generation, green electricity going to a transmission system and going into a load. In this case, it's an illustration picture of Sarnia, Ontario. We tap into that low carbon, low price electricity and feed it to fuel electrolyzers. These would be banks of electrolyzers, and they would produce a couple of off gases. One of them is hydrogen, of course, and the other one, oxygen. The oxygen goes to existing markets, and you notice that the green dash line is dashed because those markets really aren't there in any big way yet. So we take the hydrogen, we put it in a storage compartment. Now, you can imagine that hydrogen stored above ground storage tanks would be especially specific materials required to store hydrogen at very high pressures or even as cold liquid hydrogen. So we store it in a well. We will use salt caverns. This area from Windsor, Ontario up to Guelph, Ontario has a salt vein in which there are hundreds of salt caverns that are used to store all kinds of mainly fuels like natural gas, gasoline, liquid, LPGs, etc. So other people are doing this. The salt caverns are being used to store hydrogen in the US as well as in parts of Europe. So this is not that off the wall. Once the time of day changes and we need more electricity in the daytime and at a higher price, we route our hydrogen to a fuel cell or conceivably could be to a thermal conversion unit. In any case, we make electricity with this stored hydrogen so that we can sell it during peak time demands and at peak prices. So this is the scheme. The Bowman Center has been looking at this for about 3 or 4 years now. A year and a half ago, we wrote a project proposal, submitted it to Queen's University in Kingston, Ontario, capstone engineering program. The university assigned 4 fourth-year engineering students to take a look at this for us. Those students were supported by several seasoned engineers who are connected to the university, as well as from the Bowman Center. The scope of the study involved everything you saw in the previous cartoon, everything from getting the electricity off the grid, switch yards and transformer stations, the electrolyzers, the gas compressors, solution mining or repurposing an existing well, sending the hydrogen to banks of fuel cells, and then getting the power back onto the grid at an opportune time. The project, as an engineering project, of course, looked at the economics of this and time of day pricing opportunities. And the study scope also included value proposition like jobs and regulatory considerations. One of the things that was observed as the project developed was that there really is no technology risk with any of the components in this scheme. Very large electrolyzer packages are being sold today. Commercial vendors or several vendors are out there. Same with electrolyzers. Hydrogen compression is a bit of a tricky thing, but we have 3 refineries in Sarnia. All refineries have hydrogen compressors. So we know how to do that. So there really is no technology risk associated with this. But the economics are a bit of a question. And so, of course, as the project included this economics as part of the scope, the inputs, major inputs include electricity for the compressors and electrolyzers. We use a lot of water, so hot water treatment is there, and other aspects of any project, labor, maintenance, administration, etc. Those are the inputs. The outputs included green electricity, green hydrogen, selling green electricity, selling green hydrogen. Because this hydrogen is very low in carbon content or burden, there should be a value for that. Green oxygen is normally prepared by cryogenic or distillation, which is very energy intense. So there should be some green credits associated with selling quote unquote green oxygen. Not a surprise, the base economics for a $500 million project at $10, a difference of $10 per megawatt hour between purchase price of electricity and selling price doesn't make money. Now, this should come as no surprise, because if it did make money, we'd be doing it already. So the question to ask is, what will it take to make this work? We have government policies in Canada at the federal level and in several provinces to develop green hydrogen to help with decarbonizing difficult to decarbonize sectors of the economy. So what will it take to work? So for a $500 million project, the federal government has made money available for projects like this, and it's not atypical for a project proposal that has private sector support. If the private sector puts up half, the federal government would put up half. So if we can get the capital cost down because of subsidy, get it down by to 300 million, or by better engineering, and increase the difference between electricity purchase price and sale price to $20 a megawatt hour, this project would make $50 million a year, or a simple payout of 6 years, which makes this a utility grade investment. Fun fact, one of our associates, Peter Smith, analyzed hour by hour the electricity pricing in Ontario for the year 2019, so pre-COVID. And to our surprise, the price of electricity during that year for almost 7,000 hours a year would allow this $20 per megawatt hour difference in price, which makes it a policy question. The point of that last slide, I should go back, is that we are within range. The technology is there. We have the technology today. The technology risk is low, and government policy wants this to happen. This project is within range of becoming a reality. We looked at the value proposition for such a project. Now, one of the important parts of any value proposition in ESG is jobs, and more jobs. Well, this, as you saw in the cartoon, this project crosses many disciplines. So this would be, in addition to being a large project, would involve a lot of different skills: piping engineers, piping design engineers, rotating equipment, electricity, high voltage DC, low voltage DC, civil, structural, chemical. This and numerous different trades to put this kit together. Once it's operating, it will also employ a lot of people. If you were an investor, maybe it wouldn't be good to hear this, but this project will be more labor intense than, say, would a comparable 500 megawatt natural gas fired power plant. But for society at large, it will create, that's good news, because it will create lots of jobs across lots of skill sets. So what would be the deliverables from this project, and who would benefit from this project? First of all, society at large. Canada is committed to reduce emissions 40 to 45% by 2030. It's only 8 years away. This project would reduce GHG emissions by between 200 and 400,000 tons per year. The reason for the range: if Ontario's grid already enjoys a very low carbon intensity, but natural gas is used during peak periods. So if all the project did was make electricity, it would reduce emissions by 200,000 tons per year. If some of that hydrogen could be sent to displace gray hydrogen in one or more of the local refineries or chemical plants, then the emission reduction would rise to about 400,000 tons per year. This project would provide off-peak load, which is a good thing for the IESO. And when it's operating, it can provide not only peaking power, load following, and other grid services. So the electrical system operator would benefit from that. Local industry is trying very hard, looking for ways to reduce their greenhouse gas emissions. By buying this green energy, or green hydrogen, would enable those refineries to benefit by being able to report lower emissions. Because this is a large scale, the capital cost should be reduced, the economy of scale, so the investors would benefit from that. This thing in the watermark is really a battery. Functionally, it looks like a battery. You put power into it, you store energy, and then when you want the energy back, it delivers power. So as a battery, this would be very large, about 4,000 megawatts of capacity. Utilities across North America and in the world are now spending money buying lithium-ion batteries for grid services. So these are large megawatt, tens of megawatts, some of them are hundreds of megawatts of capacity, megawatt hours. One of the suppliers of these batteries has made their pricing public on their internet website, and the price works out to about $400 Canadian per kilowatt hour for a battery pack that is designed to deliver power for a couple of hours. The battery we have in mind comes in at about $200 a kilowatt hour. So we contend that as a battery, this project is already very competitive with chemical grid scale batteries. In addition to being on the price in terms of operations, a battery like this is not limited to 2 to 4 hours a day because of its sheer size. This thing could run for hours, days. The study included a seasonal backup scenario, which wasn't a lot of work done on it, but they did look at and use an optimizer and determined that a 600,000 cubic meter well would enable seasonal storage of hydrogen. Because of the intermittency of wind and solar, this big energy storage system would enable hundreds of megawatts of new wind and solar energy supplies, providing security of supply of electricity as we decarbonize our Ontario economy. With the right kind of subsidy and government policy support, this project would deliver a return on investment for the investors and for the community at large. It would, as I mentioned, create a lot of jobs. So what will it take to make this thing work? The Bowman Centre for Sustainable Energy is a nonprofit think tank. We see ourselves as a catalyst to try to get projects such as this one moving. We don't have money. We can't build this thing. We need a private sector owner to take it over, or more likely a consortium of owners because of the differences in technology. But it would be one project, not a electrolyzer project and a well project. It'd be one. That's why probably this would be a consortium. The consortium would review and modify the Queen's Report, make that report their own. Once they do that, they can then use that report as a foundation to mine for money to fill the economic gap. And by doing all of that, turn government policy into tangible assets. The Bowman Centre, of course, will make the report available and any IP associated with the report. This project, like any project, has to have the right host community. So host community for a project like this will need to have the right kind of geology, so that to build or solution mine a salt cavern. The community, because it works on electricity, you need to have access to a low carbon power, which is the case, especially off-peak power in Ontario is almost carbon free. You need a community that's receptive to large industrial development. You also need access to future and green hydrogen markets as they emerge, which is the case. All of these Sarnia-Lambton has in spades. So as a hedge, we can make electricity with hydrogen until the green hydrogen markets emerge, and Sarnia-Lambton has everything required to make this thing happen. So thank you very much. And please contact the Bowman Center for Sustainable Energy at bowmancenter.com if you have questions or would like to discuss this with anyone. Bye for now.